Hi, everybody. This is going to be a little screencast to kind of go with our PowerPoint that we have about hydrates and prepare us for our lab that we're going to do on hydrates. You learned about the definition of a hydrate from the Ed puzzle that you did. And a hydrate is just a compound that has a specific number of water molecules bound to it. We'll learn later on in our study of chemistry why water is attracted to ionic compounds and often binds itself to ionic compounds. So during this lesson, we're going to kind of learn about writing the formula or naming a hydrate, kind of a review of what you did in the Ed puzzle. We're going to calculate the water, the percentage of water in the hydrate using the formula, which would give us the theoretical percentage of water in a hydrate. And then we're also going to take a look at a set of lab data, which would give us an experimental percent water in a hydrate, because you kind of need to do both of those in your lab. And make sure that you know the difference between anhydrous and a hydrated form of the compound. So naming hydrates, it's always going to be an ionic compound with some water molecules attached to it. And you want to name the ionic compound as we already previously learned this year. So you would need your ion chart, maybe your periodic table to help you with formulas and naming. And then you add the word hydrate to it with a prefix to indicate exactly how many water molecules are bound to the atoms that make up that ionic compound. Now on page 338 in your textbook, you can see the prefixes. I did put them here for your reference as well. And they were in the Ed puzzle. So somewhere along the line, make sure that you jot these prefixes down and have them handy, because you are going to definitely need them in the lab. Part of the thing that you're going to have to do in the lab, once you determine the identity of your hydrate, is you're going to have to be able to name it. Okay. So I thought we should do an example of that. Here we have a hydrate, and you can see what we mean by having the, I just want to make sure I had a color that we could see, but you can see what we mean. There's the ionic compound, and here's the water that is attached to it. And what you do is you just name the ionic compound, like that's the sodium ion, and then CO3 minus 2 is the carbonate ion. Because this ionic compound is made of sodium ions and it's made of carbonate ions. So that is sodium carbonate. And then because there are 10 water molecules, we use the prefix deca and then the word hydrate. So sodium carbonate, decahydrate. So here's another one for you to do. Okay. I'd like you to pause this presentation and see if you can, provide the name for that. Once you've tried that, then you can restart and see how you did. So hopefully you paused it and you did practice this. Here's the ionic compound. Now, if you're using your periodic table, barium is +2, remember, because it's in the second column, it's an alkaline earth metal. Cl is a halogen, and they're all -1. And remember that instead of chlorine, we change the ending and we call these ions chloride. So we would start with that name. This is barium chloride. And then we see that we have 2 water molecules. So the prefix for 2 is di, and then we use the word hydrate. So the name for this particular compound is barium chloride dihydrate. So throughout this homework and then like labs and things, you are going to have to name ionic compounds and then refer to the list of prefixes to indicate how many water molecules are attached to the ionic compound. So let's try another one, because here what we want to do is show you how to calculate the percentage composition of water, okay, like how much of this particular hydrate is water by mass. Remember, percentage composition is by mass. And to do that, you have to have a formula. So again, this is barium, which we just had gone over. It's an alkaline earth metal, so that's +2. Hydroxide, you can find that one on your ion chart if you don't remember on your own what hydroxide is, you could look that up on your ion chart. So we need to write the formula between those two ions. I'm going to need 2 of these hydroxides for every 1 barium ion. So it's going to be barium, and then to have 2 of the hydroxides, I have to put it in parentheses and then the 2. And then it is octahydrate. So you put a dot. Oh boy, got my nice little line there. Sorry. Back to put a dot. And then octa is the prefix that means 8. And then, of course, that's how many water molecules are attached to it. So this is our formula. And to calculate the percentage of water in there, we need to do a molar mass problem. Now, when you do that, what you want to do is just treat the water like 1 unit. So, for example, we have barium, we have oxygen, we have hydrogen, and then I'm just going to treat the water like it's just 1 unit altogether. So I look at my formula. I have 1 barium, I have 2 oxygens, and I have 2 hydrogens. Now, you might be thinking, there's a lot more than that. But remember, the other hydrogens and oxygens over here, they are part of this unit of water. And I'm going to account for that because there's 8 of them. So then I need to get my periodic table and get the molar masses of the elements. Now, the water I have to add up. And it's such an easy one to add up. That's why we just keep it all together. Oxygen is 16, and each of the hydrogens is 1. So it's a total of 18. So now we need to get our subtotals for all of these different elements. So 1 times 137 is 137. 2 times 16, we'll get 32. 2 times 1 is 2. 8 times 18 is 144. And then we total it to get the molar mass for this particular hydrate. And when I added those together, I got 315. So this is the total number of grams in 1 mole of the hydrate. Okay. Now, if we want to know what percentage of that is water, okay, what you want to do, you want to take the mass of the water. Oh, I'm just kind of running out of room. Let me redo this. Sometimes I just run out of room. Okay, let me start over. So we want to do the percent of water that's in this compound. We need to do the mass of water that's in the compound over the total compound's molar mass, right? And then take that times 100. So to get the percentage of water, I'm going to take, let me get a little highlighter here. I'm going to take my 144. I'm going to divide by the 315, and then I'm going to multiply by 100. So I take the 144, which is grams of water. I divide by the 315 grams total. And then I also need to multiply by 100. Now I'm going to use my eraser here and get rid of this molar mass so that I have some space. Okay. Alrighty. And hopefully you've gotten out your calculator and done that math. But 144 divided by 315 times 100, and I got as an answer to that 45.7, and that is the percent of water. So almost half of this hydrate is made of water. Now the other 54.3% is the barium hydroxide. Okay. And you could, if you wanted to, break that down into how much of it's barium. Well, then you do 137 over 315. How much of it is oxygen? How much hydrogen? You can do that for any of them. But to identify a hydrate, what you really just need to know is what percentage of that hydrate is water, because you know that the rest of it then is the anhydrous portion of the compound. And when you do this from a formula, like when you use a formula to calculate this, We call that the theoretical, I'm writing here, the theoretical percentage of water in this hydrate, okay? And remember, that has told us what percentage of it is water, and then the rest of it is the anhydrous barium hydroxide. You did learn that word anhydrous from the Ed puzzle. That's the form of the hydrate without its water, okay? When you have a hydrate, like let's say, for example, you have that barium chloride dihydrate from earlier, you could heat it, and when you heat it, this water might evaporate and leave you with just the barium chloride. The salt portion of the hydrate that is left behind when all of the water is driven off, that is the anhydrous portion of the compound, okay? The whole thing, when you have, the water molecules attached, the whole thing is called a hydrate. But when the water has evaporated, what is left behind is known as the anhydrous portion of the compound. And I think you've seen, and we talked about the fact that for many hydrates, it's pretty easy to go back and forth. Like if they're in a moist environment, they will absorb water and become hydrated. And then if they're in a warm, dry environment, like an oven or, a desert, they will lose their water to the environment from the heat and then, the dryness in the air. So they can often go back and forth. And we're going to use that to our advantage, because what we're going to do in our lab, let's say we start with a compound that is hydrated like this. Okay. Remember, we call the whole thing is called the hydrate. So we can weigh, for example, the hydrate that we start with in a lab, and we can say, okay, we've got 10 grams of hydrate. And we can put it in an evaporating dish and we can start heating it. And as we heat it, this water portion of it is going to evaporate. So that means that the weight's going to go down, okay? And so after we're done heating it, what's left in the dish is called the anhydrous, salt. And we can figure out the difference. Like let's say I weigh 10 grams of hydrate, and I heat it until all the water is gone. And the way I know all the water is gone is I'm going to heat it more than once and compare the weights. When it quits losing weight, the water is gone. And when all the water is gone, I weigh it again and it weighs 7 grams. Then I know that the 3 grams that were lost was water, and 3 out of 10 is 30%. Let me show you that math with some actual data, okay? So here's some actual data from a lab. So we weigh the evaporating dish empty. So we got to know how much our container weighs. Then we put a little bit of hydrate in it. That would be the form with the water, okay? Now, if you take the difference between these, so what is that? 37, let me get something a little darker here. Let's take the difference between those. And I don't know if that's going to show up well either. Right with white. So 37.75 grams. That's the dish and hydrate. And we subtract out the 35.25 grams. So this is the dish with the hydrate, right? And this is just the dish. Well, when you subtract it out, let's see, get 2.50 grams. If the dish was subtracted out, all that's left is the hydrate. So this number right here, when you subtract these first two, this, and you got to look at what they are. They may not be the first two things in your, in your data chart. You better read the descriptions. But when you take the difference between the dish and the dish with the hydrate, you can figure out how many grams of hydrate you're starting with. And then the way to figure out how much water is lost, okay, let's switch colors again, is to take the difference between these two. Because here, the 37.75 grams, this is the dish and the hydrate, right? And the 36.84 grams, this is the dish and the anhydrous. Well, what the difference is how much water was lost during the heating, okay? And like I said, we're going to heat a couple of times to make sure that all of the water is driven off. Well, if I take 37.75 minus 36.84, I get 0.91 grams. And the difference here is how much water was lost, the difference between the hydrated and the anhydrous. So now I know that 0.91 grams of water was lost out of my original 2.5 grams of hydrate. So I'm just going to make a little space here. Let me get rid of some of this. Okay. And I'm going to show you then, using those two numbers, how you can calculate the percentage of water, okay, and determine if, if it was the formula that you were previously working with. So you compare it to theoretical percentages of water then and determine an identity. So to get the percentage of water, remember, you ignore that random line, you take the mass of water, I'm getting some random lines, over the mass of the hydrate, okay, and you multiply by 100. So remember, we just calculated that in this particular case, there was 0.91 grams of water lost, and we had started with 2.5 grams of the hydrate. When I take 0.91 and I divide by 2.5 and I multiply by 100, I get 36.4. Oh my goodness, that one looks awful. That we got to redo. I get 36.4% water. Now this is the experimental percent, right? Because we did an experiment to determine it. And what you can do is now take this result and you can compare it to some formulas. Like, for example, what if I compared it to this barium hydroxide? 36% doesn't match 45%. So this, the barium hydroxide octahydrate, is not my hydrate in this lab. I would have to try a couple of different formulas that my hydrate might be based on other things, like other descriptors. And in lab, I'm going to give you a list and say, hey, your hydrate's one of these. And what you can do is calculate the theoretical percent of water and each one of the formulas, and then see which one matches the experimental percent of water. And then you figure that is the identity of your hydrate. Okay. So remember, you've got the hydrate is like the whole thing. The anhydrous is the salt that's left behind. The water is the portion that evaporates off when you heat it. And you can find all of those numbers from lab data or from a formula. And then you also, of course, need to know how to name hydrates. Okay. So any questions, please see me. And when you do your lab, make sure you're looking back at this and using this as some examples.